All right, so I was interested in physical execution and data fusion. I started on the logical query planning side and just sort of following wherever this goes, and was aware of Ray. And when I found the DataFusion Ray repo, I became interested and thought that I would see how it works and what I can do with that. So a little bit about me. First, thank you for having me here, Edmondo and Andy, for inviting me. I appreciate it. Undergrad, I did CS, and then I went on to grad school and did physics simulation. After that, this was like when Linux was just becoming usable. I got to do embedded Linux for consumer audio devices, which was a ton of fun. Then I worked in audiobook B2B SaaS for 9 years, which was eventually acquired by Spotify. I moved into storage, and that was when I sort of went from the small scale and then the medium scale at the SaaS to the large scale at Twitter. And that large scale continues today at Datadog and the metrics platform. That explains my interest in data fusion. At Datadog and metrics platform, we have a existing way to query metrics at scale with low latencies. As we get asked for more and more features, general query execution becomes very important. And so understanding that and bringing that expertise to my organization is what I wanted to get out of this. In fact, a group I work with invited Andrew to come and speak with us maybe 6 months ago, just about data fusion and their experience with it at Influx. And after that, I thought, oh, I should acquire some knowledge and expertise here to help steer Datadog as we learn more about it. There's never enough time for programming at work, so I do like to program. So I usually make like toy games and other things to amuse myself. I like distributed systems. I like motorsports, and I also have a dog who is ever at my side and keeps me really busy. Okay, today I wanted to talk about what were my goals in messing around with this. Importantly, I hope to instill on you some of the learnings that I took away from working with Ray and with Data Fusion and ways to combine them that was unsuccessful, because I think that's valuable to share, and then talk about a path that looks promising. Then talk about what's next, its current status, and move on. First of all, my goal is to learn, like have fun. I was familiar with our query execution model at work. It's very rigid. When I took that knowledge and looked at the DataFusion code base and really learned about how it worked, I found it to be such a pleasure to work and read this code, because it was composed very nicely, and the abstractions that were present immediately struck me as powerful and composable. So I wanted to learn more. And particularly, my ultimate goal would be, how can we use DataFusion for low latency and high scale queries? This is possible. I want to find out. In this work, I want to reuse as much as possible from DataFusion in distributing these physical query plans. And I don't really want to rewrite anything that is already done in a physical query plan execution node for DataFusion. So in particular, I'll talk about how I handled the shuffling due to the repartition in the hash, repartition exec for hash, and I'd love to seek your feedback, Edmondo, Andy, others, about if these choices are good or not prudent, or if they can be improved in any way. I also think it's always good to have a nice Python interface, and when I demo whenever I demo these ideas at work, if I'm able to do it in Python, it really facilitates delivery of the ideas, and we don't get bogged down in any of the Rust semantics, because at work, not everyone is familiar with Rust. I also want to generate interest and collaborate with others. I'm here to meet people. I would like to move from doing this independently to working together. Okay, my journey to understand physical execution in Datadog looks a little bit like as follows. If we have this simple query, we get a physical plan that looks something like what's on the right here. And in my mind, I'm bucketing this execution model on a single node for DataFusion as like a pull model or a lazy model, in that the top of the tree, the coalesce partitions plan node, we call execute on it, and we say, give me the batches back that represent the final state of this query. It knows that its children have 2 partitions, and it will spawn 2 tasks to do this. Yes, in step 2 there. And then each child can operate independently and will call the partition of its child, in this case, the repartitioning of the hash, because if you remember, our query said we're going to count the number of colors from this table we're scanning. So we need to repartition by color. But the interesting part I discovered when reading through the code for the repartition of the hash, and it won't be a surprise to anyone who's worked with Shuffle before, is that to produce one partition result of a hash, like say only the color red, for example, it needs visibility or access to all of its child partitions to get the like red nodes out of there. And so how do we distribute this and how do we scale this was what I was trying to understand. So my first attempt was a very naive attempt. And I said, well, I want to take the same execution model that DataFusion has and naively, like, quote unquote, port it to Ray. And so I will create a node that I can insert into the physical plan that will execute the remainder of the plan in a task in Ray. And a task in Ray is just a managed process somewhere in the cluster, some compute process that you have access to. And if you don't know Ray, you only need to take away from it that it has a very simple developer interface. I think that's part of its success. That makes spawning tasks like easy and low code. So this ultimately failed because if we go back and look at this execution plan, what would happen is we'd ask the top of the node, hey, give me the batches. And then as we execute these nodes, we might encounter a Ray exec node, as I alluded. It's going to jump back into Python using the PY03 bindings, tell Ray to start a task, send the physical execution plan over there, execute it in Rust, and that process may repeat. It may spawn another task and do this. And the idea of, or the path of like going from Rust into Python, into Ray, into Python, back to Rust, into Python, repeat, 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 was complicated. And it created a lot of challenges around sharing data because the object references between the tasks, the batches were shared between the tasks using Ray objects, which are, Ray will take the output of an object in Python and store it in memory, local to the cluster node that performed the task, and share it, make it available among peers. Edmondo, did you have a question? I couldn't tell if you were raising your hand. Nope. Okay. So in the Ray documentation, they put objects fate share with the owner, and I like that tight condensed phrase. And what's important is the owner needs to stay alive. And it was very complicated because a lot of these tasks that were producing objects were ephemeral in the execution of this plan. And so they would disappear, the objects would lose. It was a mess, so I don't want to spend time on it. Unpacking this and being a little bit more deliberate produced a much more sound result. And so this is, I went back and I said, okay, I've read this book, Andy's book on how query engines work. Let me reread the section on Shuffle. Let me go through the stages or the code that's there, see why it works. And for reference, the code that is in the repo now uses a disk-based shuffle, from what I can understand. And the queries execute in their entirety. Is that right, Andy? the stages do before the subsequent stages have access to the data. Correct me if I'm
That's
wrong
correct.
there.
Yeah.
So I wanted to make the stages streaming in an attempt to be lower latency, but also in my naive model of my pull-based execution, where the top execution node creates subsequent ones, et cetera, et cetera, et cetera. Even though they're streaming results back, they have nothing to do until the bottom node of the tree gets scheduled, because it is the node that has access to the data. So I thought, well, if we break this up into stages, like Andy describes in this book, I've linked the page. And if we're streaming, we can schedule all stages concurrently in Ray, and they can stream among each other. And so now we get this pipelined effect where they can do work while the leaf stage is still executing. It may have streamed batches to upper stages so that they can make progress. And I thought, oh, this will be helpful. And I'll describe how this is, and I'll show some code depending on how we do in time. So this worked, and this is how we manage the shuffling in here. So I've tried to draw some pictures of what I understand is going on, and then the attempt to distribute it in a streaming manner without rewriting the partition hashing. So if you look here, when the left side partition from the Agar node, I don't know if you can see my mouse, but I'm highlighting it here, pulls from its child here, which will produce a stream of only the blue rows, if you'll allow me to shortcut like that. This repartition node needs access to both scan partitions to find all the blue nodes. That makes sense. So how can we break this up to execute it in discrete units? And so this is how I made an attempt to arrange it. And I'll go through this. We break the query tree up into the following Ray stages, top and the two bottom. And they can all be scheduled for execution immediately. And if you look at the top stage, the Agars, each partition has to get their data from somewhere, which comes from the other stages. And I struggled with, at first, coupling these all together and keeping sense of it all and keeping the objects alive in Ray enough for them to be exchanged. I had much better luck when I introduced this exchange actor, which is just a stateful task in Ray that lives for a long time. So the Ray stage and the exchange, all of those are actors now in Ray. So they'll spin up. They can communicate among each other with RPCs that Ray makes very high level and invisible. But when we execute the Ray stage on the left down here, how do we make it so that we find all the blue nodes without having access to both scan partitions? Because we want to be able to distribute reading the data in, especially when we're reading over many, many files. So when you send the physical plan to this Ray stage and you execute, say, partition 0 on this hash, it's going to want to see the code that's in there in DataFusion, wants to form a stream of all child hashes. So I thought I can make that stream, I can make all the child hashes invisible to the repartition exec and only show one. And that's this node here that I called the partition isolator. So when I break up the plan, I only show this node the first partition of the scan. Then we'll do another Ray stage concurrently, and we'll also run a hash exec there, and we'll show it the other node of the scan. And when we run this Ray stage, it's not the sort of pull model, it's eagerly executed. These stages themselves are driven to produce all their output. They stream output of both of their partitions to this exchanger, which is going to receive the batches. Then when asked for the partition 1, the agger, it says, give me partition 1, and I know I need to read it from, stage 0 and 1 here. And it'll get it from the exchange, and the exchange has a merged stream from both stages. I hope that's clear. This is the slide that describes how things are wired up. So if there are questions when I'm done, and I'll be done shortly, please ask on this slide, or please come back to this slide and we'll talk about it. Okay, so I can do a quick demo here. Yeah, you can see my stuff very briefly. Ray stage. Here's a ray stage. It takes a physical plan. It executes it. Oop, that's the wrong one. Let me go over here. Just a moment. I hope this format is as casual as I'm making it. Okay, the exchanger, here it is. So Ray Remote makes this a actor that lives in the cluster. That's what that decorator does. And here's what this exchanger does. It keeps a bunch of queues for the output batches, and it can receive a batch, that's this put, for a stage ID and an output partition. And you can get a batch, and that's how you stream the data out. These batches aren't batches, they're actually object references only, because I don't want to materialize the full batch in the exchanger. So I will let Ray store the batch in its shared object store near where it was created, stream the reference through the exchanger. Then at the top of the tree, when I actually need the batch out, I'll pull the reference and then I'll materialize the batch. This sounds cool. Spoiler alert, it's slow. It's not a good idea. I'll get to that. But this is like what it looks like. We're going to do a simple query here. And I will do this on a local array cluster. So startup, here is our physical plan. If you can read this, you'll see that I'm scanning a customer parquet. This is from the book, How Query Engines Work, as a canonical example. I'm scanning customer, I'm scanning orders, we're joining them, we're doing an aggregate. So I created a physical planner. We go through this physical plan and we insert some nodes here. Every time we repartition, we know we are going to shuffle. So we break this up into stages. Ray stage 3, 2, 0, 1. And we did this with the physical planner because I very much like the tree abstraction of the planners. It's so useful. And I used it from the logical federated work. But now we have this tree. We can just pull apart the stages. Whoops. And they look like this. Stage 0 is the scanning of customer. And this is exactly what's presented in the book and how you might do this in Spark. Stage 1 is here. Stage 2 is here, but you'll notice instead of consuming data from a child node, we've got this physical execution node in here called the Ray stage reader. And what that's going to do is connect to the exchange object, go get object references and materialize them and send them upstream. This is implemented in Python underneath because we need access to Ray. But what's great about this is it's easy to reason about. If you see stage 2 here, we're going to create an actor, execute this physical plan. When we get to the Ray stage readers, we'll go read object references and create them and or materialize the batches and proceed upward. There is no giant spaghetti mess of Rust, Python, Rust, Python, Rust, Python, Ray, forever. A stage only will ever be cut on the boundary of needing data from the exchanger. So all stages kind of look like this. They either produce data organically, like from a file themselves, or the leaf nodes of the stage are going to get it from the exchanger. So that's it. When you execute Ray, you can tell it that, hey, color code my different actors for outputs. You can see that each stage receives a portion of the physical plan. It knows how to execute it. Some object references get exchanged representing batches. We get our result. I print out some stats of like, for each stage, how many rows did I get from each of these batches, et cetera. For this execution here, each of these stages, 1, 2, 3, 4, was executed in its own Ray actor. And within each stage, we eagerly executed all partitions and pushed them up. If we want that scaling where we can execute not only a stage in its own actor, but a partition for a stage in its own actor, I said, okay, this needs this isolate parameter where it will tell the Ray context in the planner to say, create stages and schedule each partition in its own Ray stage. And you'll look in the plans here. Here now we have the partition isolator shown here. So stage 2 will be executed as many times as there are child partitions, and it will only see, actually, let's look at stage 0 or 1. It's a better example because they're smaller. Stage 0, we want to, the physical plan itself from Parquet, or stage 1 here, has 2 partitions for reading from this objects or orders table, but we want to spread this out among physical nodes because we might imagine that this plan has 1,000 files or something. So each one of these, we want to only show one partition from the Parquet executor. So we isolate that. So one Ray task will do partition 1, partition 2, partition 3. So we can get some scale and concurrency there. Let me go back to my talk. Where's my talk? Yeah, okay, we did the demo. Here's what I learned. It was so cool, and I was so excited about the idea, and this is the original idea. I messaged Andy, like, hey, can't we use the Ray Object Store? It's so awesome. Yeah, but if you try to really send high throughput stuff through it, it's slow. Here's why. When you save an object in an object store and you want to get it back, we create a task to do it. Andy, did you have a question?
No, I'm getting excited about some stuff that might help. So I'm sorry.
So if you stream a ton of batches, you're just going to create tens of thousands, hundreds of thousands of Ray tasks, even for a moderate sized TPCH query like scale factor 10 or something. Those tasks are going to have to wait to be scheduled by Ray. It's going to suck. It's going to be slow. That's what happens. So to mitigate this, you end up increasing the batch size so that you do less batches. It's bad. And then one that I really bogged down on for a little bit was Ray advertises, hey, we're aware of Arrow and we will play great with Arrow, and our object store will enable zero copy deserialization, serialization of Arrow batches through IPC, which we like. The problem is Ray does it by using the PyArrow bindings behind the scenes. Those are the C++ bindings. When I try to deserialize it on my end, I use Rust. This causes problems with alignment of IPC in the data. And I know this is a known issue that folks here have commented on. And I think I'm using all of the latest versions that should have the fixes in Arrow RS and things to accommodate for this, but I still encounter this alignment issue. Once I understood that and I could verify that I was encountering it, my solution is to don't let Ray do its magic, but handle the IPC serialization, deserialization myself, and use Rust on both sides, and it was better. So something I learned is that we still have this exposure and seam between C++ and Rust here, even though I think we've addressed it with an extra copy in the AeroRS code right now. We still have it. I don't know more about that, but I just know we have it, so I thought I'd surface that as a learning. Okay, it was slow. Original ideas in the DataFusion Ray repo and its issue commentary were, oh, maybe we can use Aeroflight for streaming between them. I wanted to have more demos and better slides, but I was hacking all weekend on this and I got it working, which is great. So now I could stream directly between stages, but the complicated coupling hurts my brain a little bit. It's still easier for me to have this intermediate exchange actor where I route stuff through, and it more easily let me transform what I had into flight. And anyway, it's fast and it's flight. I haven't benchmarked it yet because I know I'm hiding a bug in there that I'm trying to find, but it's much faster. And when you look at Ray and you look at its performance, like monitoring output, it'll only create as many tasks as you have stages and partition to schedule. Maybe one for an overall supervisor, one for an exchange object, and that's it. No more 100,000 tasks. All the communication is done by Aeroflight. And it was great. So I changed the Ray stage reader nodes to, instead of going to get into Python and go grab a batch from the exchanger, just connect to the exchanger using Aeroflight and pull a batch that way. And now the exchanger advertises itself on Aeroflight. And once it's up and advertised, let me show you the code. Here's the exchanger. So this Pi exchange is in Rust, has an Aeroflight interface. Now our Ray exchanger is much shorter. All we need to do is be able to respond with what IP and host we're on within the cluster. And we run this serve, and that's it. A Ray stage object is now much shorter. So a lot of the Python code went down as it moved into Rust more. So we get a stage, which is a physical plan and things like this. And we eagerly execute its partitions. And when we execute them, the Pi stage object, as it's called here, streams results to the exchanger. So now we have this picture, but Aeroflight, as all the lines are Aeroflight when they cross a boundary, a dotted line boundary. This looks, but I still have this partition isolator to be able to reuse the partitioning hash. This approach also works for partitioning round robin. You can drop a round robin hash in there. It works the same way. What I like about this is all the DataFusion moving pieces are the same. We just used a planner and physical optimizer to insert those, readers where appropriate, to just really wire things up. And we do this little bit of hiding of these to make sure we can scale out our initial reading of the data. But I think it's going to be good. Is it going to be the pinnacle of performance? No, because Ray, when you execute this, you have to spin stuff up in Ray. Like, hey, I'm going to do a query, start a supervisor, start an exchanger, start the stages. But what I want to demo about this is the actual execution in a distributed way can be fast. And where I need help here is the physical execution nodes have a lot of metrics that they collect. In my implementation, I eschewed implementing all of those just because I don't have time to learn it right now. I'm going to make it work, then I'll instrument it back up. If someone understands that stuff well and wants to instrument it, I think the code's in a place where you could totally plug it in and we can understand more where the slow parts are. I also haven't thought about how we aggregate metrics across distributed stages. Maybe we send them through the exchanger in another way, have some way to send them through the exchanger. That would be cool. Okay, now what? We've got a performance benchmark. I know I've got a bug hiding in there. I've got to figure it out. Make error handling consistent. I might be throwing DataFusion internal error here or an unknown error here. If it's going to be publicly consumed, like you got to have a tight, well understood and intuitive interface that can be cleaned up. Tidy up the code organization. I think yes, when it's beyond, does it work to, if you want it to be consumable, move things around a little bit, document, and then also, I would love to collaborate on this. I think the machinery is good, and I think the abstractions I chose of how to break it up makes sense, but I would love to hear if they don't. And yeah, that's it. Thanks for your time. Appreciate it. I went a little longer, Andy, than expected. I maybe went 30 minutes. Sorry about that.
Well, that was awesome. Yeah, thanks so much, Rob. That's a great presentation. To answer just one of your last things you said, so if the metrics in Ballista, we do that kind of aggregation of metrics. Honestly, I actually don't remember right now how that was implemented, but that might be a good place to look to understand the approach that was taken there. I don't know if it will fit, but
yeah, I need to be able to quantify how good this is, and my goal is, if this is good, executing physical plans separately, exchanging data through Aeroflight. One of the things we could do is remove the exchanger and make it more of a library that's inside the Ray stage reader exec on each node. It complicates discovery and routing a little bit, but it's totally possible to skip a hop. And the next thing we could do is, rather than spin up workers and things on demand, spin up a fleet of them, and then just have Ray distribute work to already instantiated workers just to save the lead time. I'm really, really interested in like how low latency can you get responses? Because for my work in observability, low latency is important. The leading edge for us is such high volume queries that we have specialized solutions there. And I would really love for it to be more general and integrated with the rest of our time where we keep queries or where we store data. I would love for the query interface to be more seamless inside Datadog and not bespoke based on when you are asking for data. Like, I would love to build a physical or logical plan and have that guide all of the places that we do this. But I really need to see how low latency this stuff can get. And this is just the beginning of that exploring. Andy, you said you had stuff that maybe could help. I'd love to hear about it.
I'm particularly referring to the Arrow IPC code, which is like the lower level pieces of doing that serialization. It's used in both flight, but also what you were talking about, passing it back and forth to C to C++.
Yeah.
The good news is that code has a lot of like low hanging fruit, I think, to improve. Like a couple of copies to get rid of. Well, I don't know about a couple of copies, but I feel like the pieces were there, but it wasn't necessarily documented particularly well. The other thing it didn't allow you to do is to just say, trust me, this stuff is valid, and turn off validation, right? Which might or might not be relevant to this case. But basically, if you're sending data from trusted nodes and you're receiving it from the same trusted node, there's no reason to like go revalidate all the data, which the current code will do. Like, it'll literally go through and make sure that it's all valid Arrow. So that's what I'm referring to in particular. I left a couple of links in the chat, but someone else showed up and said, hey, this is actually quite the Arrow Rust IPC implementation is slower than C++. Why? And we dug into it. One big part of it is because it's revalidating everything all the time, even if you like trust it. The other thing recently is I think it was possible but not clear how to mmap files, which I don't think, that's not relevant, I don't think, to this particular case. But I think we just did an example of how to like mmap a file and then immediately turn that into Arrow record batches without having to copy the data again. So that, so I guess like a couple of pieces like that, I'm feeling like the Arrow IPC libraries might become easier to use in a more performant, even just so.
Yes, let me show the Python interface here of what this looks like. First of all, the FFI issue of passing objects back and forth is a little clunky with Python and Rust, but it's mostly good. So we create array context and pass it a couple of parameters. We can't pass in a config because the Python won't recognize it as the same type. So I just exposed this set here, have a query, but have the same interface as the rest of DataFusion. So create a data frame. The array context knows how to run a physical optimizer to break up the physical plan. And this isolate partitions parameter allows you to, it'll do that, insert that partition isolator, as I said. But, and then show. It does have this extra method on the data frame called stages, where you can actually get the list of physical stages back and print the discrete physical plans, because that's useful. But it looks like the rest of DataFusion. It's not a surprise. And this is important to me when I think about internally here. A possible landing space for this work is it will inspire more work on low latency, high throughput stuff, which would be more leading edge metrics observability queries. But if it doesn't get to the pinnacle of scale and latency that we will require at work, this probably can find a home in our ML ops groups who are already using Ray clusters, who are already using DuckDB, DataFusion, but mostly they live in Python. And if they can have a way to interact with some of our larger data sets and use our catalogs with this interface that is like single node DataFusion, I think they will be happy. They're always asking for higher level access to broader amounts of data and doing more queries, and our Spark interfaces lag behind always, and so they end up doing workarounds themselves just to be able to work with modern tooling like Python and DuckDB and DataFusion.
I'm particularly excited about some of this work because it aligns well with, I think, what a lot of other users are doing. Right, like you're not the only one who cares about passing data quickly over the IPC boundary or over the network or Arrow flight. So spending more time optimizing those things, I think there's a lot of leverage to be gained there for the broader community, right? Obviously, it'll help this project, but it's, I think, a much more impactful way to spend time than just this, which I think makes it a good candidate to try to rally around.
Oh, good. I'm excited. I just really enjoyed hacking it. Like, I literally couldn't put it down. DataFusion's a pleasure to work with, and then Ray is also a pleasure. So, like, combining these is just really fun. One thing you'll note here is the physical plan that's presented at the top. When we break it into stages, we need to insert coalesce batches on the output of the stages for two reasons. One, we don't want to send ultra tiny batches over the network. But two, I found out when I switched to Flight, the other way is true. We don't want to send too big batches. Flight has a cap on byte size in batches. I don't know how to constrain the byte size, but I do know if you add this fetch parameter to the coalesce batches, it won't say, hey, try to get the target minimum number of batches. It also says my fetch number is the target maximum number I want. So it's a little bit of a magic number and some awkward tuning right now. If you specify a bigger batch size, you'll blow up Flight with too big messages, because the batch size is number of rows of my batch, but the byte size of the payload depends on the width of my table. So I haven't figured that out yet, but it's worth noting that you put it in there.
We hit the exact same problem. There's some, I'm pretty sure there's a metric, I'll dig it up for you, on the thing that creates Flight encoding, whatever. Sorry, we also hit this problem where like you basically blow out, there's like some sort of 4 megabyte default frame size or something in gRPC that we would hit if we were careful. Let me think that there's definitely an API to set that. Hang on.
Okay.
I thought we.
Yeah,
I'll post it in the chat.
Okay, I should make sure I share this. I wonder if you guys can get this. Let me put this in the chat here to see if you are able to see this link or if I need to do something. Can someone give me a thumbs up or thumbs down on if this link works? Oh, I see. I get a cool share here. Yeah, so I think it's shared with all the emails of the folks who joined this meeting, but a thumbs up or thumbs down on if it works would be useful, and I'll try to remediate the issue. Okay, cool. It works. I see people on there. Mostly, I think it's useful for reference, but also my contact information is on the first slide. So reach out to me, but I'm also in Discord, in our Discord chat now too. Hanging out in the DataFusion Ray place. Oh, I mean, for the purpose of generating interest, here's the physical optimizer. We get a physical plan. We've got to figure out what to do. So, was that right? Yeah. If we walk up the tree, and if we see a repartition, we insert this raise stage object. That's it. Then, when we're asked to generate stages, which the data frame does, it walks the plan. So, step 1, walk up the tree from the leaves to find stages. So, if we find that raise stage, we create this Python object that we can call to execute it because Ray will need to instantiate that. If we have to isolate the children, we insert that node. We insert the coalesce as you saw. Finally, we add our remaining coalesce. And then lastly, we need to know how to go get the data out of the completed query plan. And the last stage is also going to stream to the exchange. So the data frame just needs to execute a simple plan of reading the race stage data out of the exchange. So that's all of that is there. Yeah, that's it. It runs all of the TPCH queries, but doesn't get the right answers right now because there's a bug somewhere with like, I don't know, I'm closing a channel too early or something in the exchanger and dropping some data. So I just have to find it. But importantly, it can parse and distribute all of those plans. And all of the stages that it create look reasonable to me for scaling out.
If your plans aren't generating all the output, it might be the fact that you put a fetch on the coalesce batches. I think fetch like basically is like a limit. It just stops generating output after a certain amount.
Oh, that would make sense because I observed this problem when I ported this to Aeroflight beyond the thing, and that's when I had to introduce the fetch for the. Okay, well, how can I constrain the size of batches then?
I posted the URL, the API in the channel.
Yeah.
But I don't exactly know how you're building the output stream, but like it doesn't constrain the batch size. It constrains like the encoded version of the batch, which gets sent over flight. So I don't exactly know what error you're
I'm just
hitting.
wiring up. So oh god. Okay. Now we venture into a little bit of the code that might look more rough, but here we go. So let's look at the exchange.
Yeah. Oh, yeah.
The exchange needs to, here's a get stream. So this is being called by a do-get method in Aeroflight. And I'm only implementing do-get and do-put, and I'm exchanging parameters in either a flight descriptor or a ticket. And I'm not doing the sort of back and forth. I'm not leveraging all of flight, but I'm just leveraging its ability to do wire up these IPC streams, and hopefully the underlying implementation skips a copy for me.
Yeah, on line 22, you're using the flight data encoder builder thingy, and you're not setting any extra things. So I wouldn't expect it to.
Well, that's why.
In other words, there's no obvious problem that I can see.
Yeah, internal here is a channel, and so we're getting a batch, and we're yielding it in this little stream macro, and then so now our stream is record batch and flight errors as required, and so we send that to the flight data encoder builder, and the only way I have to constrain the size of the batches in the stream is to use that coalesce in the physical plan. But if you're telling me there's a way outside the physical plan, awesome.
Well, I'm looking at, the first thing I would have thought works is like the flight data encoder builder thing should have just handled it, but clearly you're saying it doesn't. By default, it should already limit the sizes that it sends.
Yeah, I don't know if I can do one.
I got to go in a couple minutes, but like another thing you can try to do is you can split the batches directly here, right? You've got that stream that's getting a batch. There's a method on the batch called like slice or whatever, so you can literally like slice it down into smaller pieces, like smaller row counts. And I think there's even there's a method called like there's a couple of them, but there's ones that will give you estimates of the memory size.
Yes, I saw that.
So you could maybe between that and slice, you can calculate what you want.
I'll just put in another like little stream hop that will slice. Composing the streams is pretty nice. Once you can translate one to another, they just sort of plug in, which is great.
Yeah, there's like I feel like there's a serious barrier to like getting streams working the first time in Rust, but once they work, they actually do compose nicely.
Yeah, I mean they're getting the types and the compiler to play nice, but that's also part of the benefit because when it's that thing when it compiles it works, which is pretty good. Okay, I don't want to take long enough that I avoid like Andy getting to wrap it up and make an abrupt ending. Thank you so much for having me. I will do another one of these if people are interested on federated queries, sending around substrate planes.
That would be awesome.
Yeah, that's great. Thank you, Rob. I'm going to follow up on Discord. There's, I wouldn't say overlap, but there's a lot of similar challenges we have in Comet around shuffle performance. So I'd love to chat more.